was Na and Cl. So Na has an electronegativity of 0.9, and chlorine is 3.0. 0.9. So the difference there is 2.1. So that's an ionic compound.
I have a question for you.
Yeah.
What if it's exactly 0.4?
Well, that's a tricky question because a lot of people think it's got to be some hard and fast box, and the reality is
it's kind of mushy.
It's a mushy system, and 0.4 is sort of ish, and it's really more of a continuum.
Yeah.
As you go across this, you get more and more ionic,
Yeah.
or more and more polar, and so it's not like it's just either or. So it doesn't fit in a box in that
Yeah.
sense. It's more of a continuum, we would call it.
Yep.
So that's kind of a good question there, Mr. Sams. All right, now. There's polar bonds where the electronegativity is less than 2.1 and greater than 0.4, and there's also a polar molecule. Now, to be a molecule be polar, you must have two things. The bond must be polar.
Yeah.
If you have a non-polar bond, you cannot have a polar molecule. But you also have the shape must not
cancel out.
And we're going to learn more about shapes in a subsequent podcast. So, but let's kind of get that on the table here for you guys to go there. I guess we should do that now.
Yeah.
All right. So polar molecules. So examples of some polar molecules. The classic example is water, HOH. And I'm not going. I'll tell you the shapes when we do the shape discussion a little bit later. But water has this bent shape.
Yeah.
And O has a value, oxygen. Let's go
2.4? 3.5.
3.5. So this number here is 3.5, and each of these were 2.1 if you recall. And the difference there is
1.4.
1.4, so that makes it a polar bond.
Yep.
And because of the shape, it's going to cause this to be polar, meaning I put the positive. Actually, what you do is you try and find the center, the geometric center of positive and negative charge. Since the O is more electronegative, it gets a slightly negative charge. The hydrogen slightly positive. And you ask yourself, where's the center of negative charge?
The oxygen.
It would be on the oxygen because, of course, that's the only thing that has negative charge. So this is negative. The geometric center of positive charge is right here in the middle. And guess what? I got a positive here and a negative here. I've made a little magnet, haven't I?
Yep, a little dipole moment.
A little dipole moment, we would say. Yeah. Another example of a... Yeah.
Oh, hey, look at that.
Yeah, I actually had a chart here.
Picture.
Picture much better than my little sketch. But you can get the idea. The geometric center is right here for positive and negative here. And notice I have the dipole moment. Actually, notice how the charge is drawn this way. All right. Now, here'd be another example here, ammonia, NH3. Ammonia has a pyramidal shape, and these are the positive ends, if you look. And then if you go right in the center, this is where the center of positive is, and the center of negative charge would be right on the nitrogen, because...
It's negative.
And notice that, are those in the same place? Is the positive and the negative in the same place?
Oh, no.
So this makes this a little dipole.
Yep.
And then they draw it this way with this little red arrow thing you can see. Now we have a different ballgame with carbon dioxide. See, we have slightly negative, and this is two slightly positives. So where is the center of positive and negative charge? They're actually both on the same place. Yeah. This is positive and negative, and that makes them cancel out. And that makes this non-polar, or not polar right here. Okay? That's not an important screen. All right. We should talk about ions and size.
We should, yeah.
Okay, last topic here.
Because it all matters.
Yeah. All right, ions have different...
yes, different sizes than the atom that it came from.
So, if I have an atom...
We talked about this a little bit in the last lesson.
Yeah, if you've got an atom,
this
like
is the babysitter and kid thing.
Sodium, and then I become a sodium ion, turns out this size of the sodium positive 1 is smaller.
Yep.
And so this is actually an example of a cations. Cations are ions with a positive charge. Cations of the same element are smaller.
Because there's more positives in the nucleus than there are negatives outside, so it pulls them in.
And anions of the same element are
larger.
Larger.
Because in this case, there's more negatives on the outside than there is positive in the nucleus, so they're spread out further.
So let's say I have nitrogen, and then I have the ion of nitrogen that's most common is the nitride ion. It would be much bigger. So in this case, you've got, your analogy with the babysitters.
Yeah.
Nitrogen has seven protons, and then you would have 10 electrons. So you've got 7 babysitters trying to hold on to 10 kids, and that's a lot harder than 7 and 7.
Yep.
So that's how you can know that. And there's actually a chart. Draw pictures. We did this. Okay. And here's a chart here. This is the size of the lithium ion and the beryllium positive 2, O negative 2. So the O's would be like small, and for the lithium atom, he would be much bigger than the lithium ion. So the purple ones are bigger than expected. No,
Yeah.
the purple ones are smaller than
Oh
expected.
yeah, sorry, you're right.
And the orange ones, as pictured, are larger than expected.
What's the next slide?
You know, an important word, folks, that's not in your handout that you should add is this word. Everybody write this word: isoelectronic. Sounds like some fancy electronic part in your computer, doesn't
Yeah.
it? But it's not.
No, iso means same. Electronic means electrons, so we have the same number of electrons.
Okay, so a way to look at this is if I've got a sodium ion, it has how many electrons? So
It has 10 electrons. 'Cause
How
the
did you get that?
Well, the sodium atom has 11, and the +1 charge means it lost 1, so it has 10.
All right, what if I have magnesium plus 2?
Well, it normally has 12, and it lost 2, so it also has 10.
Oh, same number. That's pretty
is,
interesting.
yeah.
What about, say, the fluoride ion?
Okay, it normally has 9, and it got an extra 1 for the negative charge, so it has 10.
I'm thinking we're seeing a pattern here.
I do.
What about the oxide ion, O negative 2?
Normally has 8, got 2 extras, for a total of 10.
Okay.
And hey, let's throw neon in the mix while we're at
Okay,
it.
neon.
Neon has 10.
Now there's no charge, so we have to play the game.
Right, so all of these have the same electron configuration as neon, and they all have 10 electrons, so we call them isoelectronic. But the difference with these atoms is they have different numbers of protons.
Right.
So, since they have different number of protons but the same number of electrons, they're going to have different sizes. So if we go back to that table, and we compare the ones we were just looking at, the sodium and magnesium and oxygen and fluorine, the one that has the least number of protons is the biggest. And why would that be, Mr. Bergman?
That would be because, of course, it has the least number of protons. So it's there's less babysitters holding on to the 10 kids.
Right.
And the smallest one would be, of course, the magnesium,
Magnesium.
because he's got the most babysitters hanging on to the same
10
number of
kids.
kids.
Right,
Or we
exactly.
could even go one more step further. Aluminum's even smaller. We now have 11.
Yeah.
Yeah, 11.
Yep.
11 babysitters holding on. No, not 11. 13 babysitters
yeah.
holding on to 10 kids. And
We're good at
they're-
counting.
Yeah, we're really good at that.
That's why we do science.
All right, rank the following order from smallest to
I
largest.
think we just did.
These are the ones we just did.
Those are the ones we just did.
So let's go back and rank those.
Yep.
So who would be this? Who'd be the smallest to
Smallest
largest?
would be magnesium.
So magnesium, because he's got the most positive
Most
charge.
positive, then sodium.
So he'd be number 1,
Yep.
and sodium would be number 2.
And then neon,
yeah, he'd be number 3,
and then fluorine, and then oxygen.
4, and then 5.
Yep.
Yep.
Okay.
That's it. All right. So, Mr. Sams, I think we're done. Pretty quick little podcast.
Yeah, I think so.
Not too bad. So we'll see everybody in the internet land and Ori class, whatever it might be.
Perhaps.
So we will see you all. Have a good day.
Remember to share.
Share. Where's your tape? Just don't put it on me. Don't. Oh, there you go. Not me. What